Hello and welcome to all students. In this lecture, we learn about divisibility in Z and discuss about the point least common multiple, or it is also known as LCM, 7th point, and we discuss about the fundamental theorem of arithmetic and some examples. Okay, so let us start the define the least common multiple LCM. So definition is an integer m is said to be a least common multiple of two non-zero integers a and b if, once again, an integer m is said to be a least common multiple of two non-zero integers a and b if there are two conditions. First condition is a divides m and b divides m, and second condition is if a divides k and b divides k, then m must divides k. So this is the very simple definition of least common multiple. So here the two integers a and b are given, and we are saying that m is the least common multiple of integers a and b if m must be in multiple of a, means a must divides a, and m must be in multiple of b, so b must divides m. Okay, if k is in the multiple of a and k is in the multiple of b, then k must be in the multiple of m. So this is the one way to understand the definition, or first condition we can say that uh, m must be a common multiple of a and b. See here, first condition says that m must be a common multiple of a and b, and the second condition says that if there exists a common multiple of a and b, say k, then that k must be in multiple of m. Then that k must be in multiple of m. Then and then we say that m is a least common multiple of two integers a and b. We note that a least common multiple LCM of a and b is denoted by the notation into the square bracket a comma b. Okay, so let us consider the one example on least common multiple. So this example gives the procedure to find out least common multiple of given two integers. Here two integers are given, which are 6 and 5, and we have to find out the least common multiple of 6 and integer 5. Okay, first of all we find the multiples of number 6. So we have written here the multiples not all, but some multiples of number 6. So first is 6, 12, 18, 24, 30, 36, 42, 48, 54, 60, 66, comma dot dot dot. In this way we can write many all multiples of we cannot write all multiples, because the list of the multiples of 6 is infinite. Okay, so in this way we write some multiples of 6 here. Similarly we write the multiples of number 5. So first multiple is 5, second is 10, next 15, next 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, comma dot dot dot. So now among all these multiples, now we find out, or we write the common multiples of 6 and 5. So we make a list of common multiples of 6 and 5. So list is 30, comma 60, comma dot dot dot. There are lots of common multiples. We have written 2 only. Now among these all common multiples, we have to find out what is the least common multiple of 6 and 5. The list means we have to find out the minimum of all these common multiples. So minimum is 30. So list means minimum. So 30. So least common multiple of 6 and 5 is 30. Thus LCM of 6 and 5 is 30. So and 5 we have to write here. So 5 is not written. So therefore LCM of 6 and 5 is 30. Therefore in the next line we have written LCM of 6 and 5 is 30. Okay, so this is the very simple procedure to find out the least common multiple of given two integers. Least common multiple of given two integers. Okay, now we write here the relation between GCD and LCM. The most important relation between greatest common divisor and least common multiple of two positive integers a and b is given by GCD of AB into LCM of AB is equal to product of A and B. So this is the very simple and very important relation between GCD and LCM. So if we know two numbers and if we know the LCM, then we can find out GCD, or if we know the GCD, then we can find out LCM by using this relation. That relation is very plays very important role. Okay, so once again what I am saying, if we know two integers a and b and also we know the GCD, by using this information we can find LCM. Okay, or if we have two integers and we know the LCM of these two numbers, then we can find GCD by using this relation. Okay, so that's why this relation is very important. Now next we state here the fundamental theorem of arithmetic. So that theorem says that every integer n greater than 1 can be expressed as a product of positive primes. Further, these expressions is unique except for the order in which the prime factors occurs. So this theorem says that any integer greater than 1 can be expressed as a product of primes. That's it. Okay, that can be expressed as a product of primes. So let us take one example here. Express 1350 and 1176 as a product of primes, as a product of the same prime powers as a multiply. So first of all we express these two numbers as a product of primes. In answer we can write the prime factorization of number 1350 as 1350 is equal to 2 into 3 square, 2 into 3 raised to 3 into 5 square. Similarly, we can write the prime factorization of number 1176 as 1176 is equal to 2 cube into 3 into 7 square. So this is the prime factorization of given these two numbers. Now we come to the next part. We have to express these both numbers as a product of same prime powers. Okay, see here in the number 1350 there is no prime number 7, and in the number 1176 there is no prime factor 5. So we adjust these two prime factors. So in first equation we adjust 7 by writing its power 1, and in second equation we adjust prime factor 5 by writing its power 0. So anything raised to 0 is 1. So 7 raised to 0 is 1. So there is no change in the prime factorization of first number, and 5 raised to 0 is also 1. Therefore there is no change in prime factorization of the second number. Therefore, so in this way we expressed here given two numbers as the product of same prime powers. Now let us take example number 2 now. If a, b, c are integers such that a divides b plus c and a divides b minus c, then prove that a divides 12b minus 18c. So it is very simple. Okay, so example I have solved here is quite complicated, but if we use the another method to solve this problem, and that method will be very easy, and it will give our answer in 2 or 3 not more than 5 steps. Okay, no problem, but we have written here the answer in the different way, and that is also correct. So given that a divides b plus c, there exists an integer k such that b plus c is equal to k. So this is the definition of divisibility, and by using definition of divisibility, a divides b plus c, it will imply there exists an integer k such that b plus c is equal to ka. Similarly, also given that a divides b minus c, this implies there exists an integer m such that b minus c is equal to ma. Okay, multiply to equation 1 and 2 by 6. So if I multiply by 6 to equation 1 and 2, you will get 6b plus 6c equal to 6ka, and fourth equation you will get is 6b minus 6c is equal to 6ma. Okay, so keep in mind all these three equations, all these four equations we will use in the next slide. Adding 3 and 4, if we add equation 3 and 4, you see here equation 3 is here and 4 is here. If we add 6c and 6c will get cancelled, there will be 12b and is equal to 6km plus 6ma. So 12b is equal to 6a is common, k plus m. Now subtracting equation 3 and 4, after subtraction we get 12c is equal to 6a into bracket k minus m, and this implies 2c. If we divide by 6, then you will get 2c is equal to a into bracket k minus m, and multiply this equation by 9. So you will get 18c minus 9a into bracket k minus m. So if we take a subtraction of equation 5 and 6, you will get 12b minus 18c is equal to 6a into bracket k plus m minus 9a into bracket k minus m. So if we simplify this right hand side, after simplification you will get 12b minus 18c is equal to a into bracket minus 3k minus 3m. So let us call r, we give a notation r to the integer minus 3k plus minus 3m. Therefore finally second last equation is 12b minus 18c is equal to ar, and r is the integer. So by using definition of divisibility, we can say that a divides 12b minus 18c, and that is our example, that is our the solution. Okay, so let us take the next example, question number 3. If p is a prime number, such that p divides a and p divides a square plus b square. If p is a prime number such that p divides a and p divides a square plus b square, then prove that p divides b. Okay, we write the answer given that p divides a and p divides a square plus b square. Therefore p will divide a square. As p divides a, p will divide a square, and also given that p divides a square plus b square. Okay. So this will imply p divides a square. So take a subtraction of these two things. P divides a square minus a square plus b square, and this will imply p will divide b square. A square will get cancelled and it remains only b square. So p divides b square. But p is a prime, therefore p divides b square gives p divides b. Okay, so this is the property of prime number. P divides b square, it will give p divides b. So this example is also over. Okay, so in this way all examples are over, and if you have any query, you can contact me and you can ask. Okay, let us stop our lecture here, and thank you very much.